Welcome learners to Black Slides Online Secondary School. This is our YouTube channel where from time to time we present to you lessons in Msce sciences such as physics, chemistry, biology, and mathematics. So let me welcome you to today's lesson. We continue with the topic of digital electronics, and in particular today we are going to be looking at a process called rectification, which comes in two forms, namely half-wave and full-wave rectification. Right, so like we say all the time, by virtue of being a subscriber to the channel, you can also request private tuition on the number shown here. All you have to do is send us a text message expressing interest to join our Black Slides Online Secondary School, where you have access to a full Msce curriculum. Right, so without further ado, let me welcome you to today's lesson. We are going to be looking at the application of PN junction diodes. Right, but if you are new to the channel, let me humbly request that you like, subscribe, and hit the notification bell, so that every time we post a new video, you become the first one to know. Alright, so that's very important. It's important that you subscribe to the channel for you to get timely updates. Every time a new video is uploaded, you should be able to be notified. So once again, we are going to be looking at applications of junction diodes in rectification. Remember, from lesson number 3 of the topic, we looked at the PN junction diode and its action. We mentioned that a PN junction diode is capable of conducting electric current only in one direction, or when it is connected in what we call a forward bias mode. To connect a diode or a PN junction diode in a forward bias mode, it means that the N part of the diode is connected to the negative terminal of the battery, and the P part of the diode is connected to the positive terminal of the battery. So that is called the forward bias. And a diode can only conduct electricity if and only if it is connected in a forward biased mode. If it is reversed, such that the N part of the diode is connected to the positive terminal of the battery, and the P part is connected to the negative part of the battery, then it is not going to conduct. It is said to offer very high resistance to the flow of current, such that it will not conduct. Right, so that behavior of a PN junction diode is used in what we call rectification. So we shall define the term rectification and look at the different types of rectification. So let's offer a definition of rectification. We define rectification in this application, rectification, as the process of converting an alternating current into direct current. the process of converting or changing an alternating current into a direct current. But what is an alternating current? Okay, in case you are asking that, an alternating current is current which flows in two directions, namely in negative direction as well as positive direction, or either way, positive direction and negative direction, like this. Okay, so if we have a function of voltage versus current, alternating current will flow like this. It will flow like this. So at one point it is positive, at one point it is positive, or it flows in the positive direction, which is the upward direction according to this wave. At one point it flows in a negative direction, so it goes positive and negative. Such current is called the alternating current. All right, so a diode is capable of changing this behavior of current so that it flows only in one direction. In case you are asking why anyway, why after all, why should current be converted, alternating current be converted into direct current? The majority of the appliances in your house, such as TV, hi-fis, many other electronic devices, laptops, work with direct current. So on their circuit boards, there are diodes that have been fitted into them, so that alternating current which you tap from the socket, from the ESCOM power, into your laptop, into your TV, is changed to direct current, which is needed by the appliance to operate properly. Without diodes, your appliances may not work. In fact, they can easily be blown off, because alternating current is not adapted to be used in such devices, such appliances. So there is need, therefore, for diodes to convert the alternating current into direct current. So this job is done by PN junction diodes. Right? So what a PN junction diode, once connected in a circuit, it is going to remove the lower part, this part here. It's going to remove this lower part, so that in the end you have direct current. Direct current now is going to appear, or to present to you, a waveform of this nature, like this. Right? So that's the lower part, which is the negative part, has been cut off, has been removed by the action of the diode, conducting, because of its tendency to conduct current in one direction. So it cuts off, the diode or cuts off or remove the bottom part, which is this part here. That's what a diode can do. The lower part is removed, so that only the positive part remains. All right, so that's what you call rectification. So they can ask you in a 1-mark question, define the term rectification. It is the process of converting an alternating current into direct current. Okay, so devices that are capable of doing that are called rectifiers, by virtue of the job that they do. Okay, because a diode rectifies, so it is called a rectifier. And the rectification of alternating current is done by circuits, special circuits, which we call rectifier circuits, in which the main components are diodes. Right, so we have diodes connected to such circuits so that they change alternating current to direct current. All right, but one would be asking, why using a PN junction diode? Why not a capacitor? Why not any other device? All right, so a PN junction diode is suitable to use as a rectifier because of its nature, its behavior. Okay, remember that when connected in a reverse biased mode, it offers very high resistance to the flow of current. But when it is connected in a forward biased mode, it has low resistance so that it allows current to flow in one direction only. All right, so we are saying a PN junction diode is suitable as a rectifier because it conducts current in one direction when it's in forward bias mode, and it does not conduct current when it is conducted or connected in a reverse bias mode. I've already explained what it means by reverse bias and forward bias. So a diode only conducts when connected in a forward biased mode. All right, so there are two types of rectification. We have what is called half-wave rectification and full-wave rectification. We shall discuss both of them so that you are familiar with how to explain how each rectification process is done in an exam. A question can come in paper 2 or paper 1 in section B or paper 2 in section A to ask you to explain half-wave rectification, explain half-wave rectification, or explain full-wave rectification. So we are going to go through the process of each rectification so that you should be able to answer questions like that. All right. Okay, so we are going to begin with the half-wave rectification. Okay, so in order to achieve half-wave rectification, a single diode, take note, a single diode or one diode is connected in a series with the load. Load, you think of load as anything that requires electricity in order to function. So in our case, the load is simply a resistor. We have labeled it the letter R and then subscript L. L here depicts load, so it's a resistor. So we are saying to achieve half-wave rectification, a single diode, one diode, which is this one here, is connected in the same path or in a series. Series means in the same path with the resistor. Okay, and then the rest of the circuit is just a step down transformer. So we have a transformer here. Remember, a transformer has two coils, namely the primary coil and the secondary coil. Okay, so we have a primary coil which has more windings or more turns than the secondary coil, and then an alternating current is supplied into the primary coil which has more turns, because remember we are using a step-down transformer. In a step-down transformer, the primary coil has more turns than the secondary coil. So in short, this circuit is made up of a diode, like I mentioned, which is connected in the same path with a resistor, and then we have a transformer. This is a symbol for transformer. So current is being supplied into the primary coil. Remember the action of a transformer. when current is introduced into the primary coil, it is going to induce an EMF through mutual induction into the secondary coil. All right, so think about this. When the current is introduced into the primary coil such that another current or EMF is induced in the secondary coil, we can consider one end of the secondary coil to be at a higher potential than the other. Or put simply, we can consider one end to be positive and one end to be negative. All right, let me have a proper positive sign here. So you can consider this end to be positive or more positive than the one below. So this is what is going to happen. All right, so if you look at your the diode, if we look at the diode, remember diode has a positive terminal and a negative terminal. Okay, let me show this clearly. Okay, so we are saying that one end of the diode is positive, the other end is negative. Now, with respect to the diode, the positive end of the diode is connected to the positive end of the power supply, in this case of the voltage source, or the region which has higher potential of voltage. All right, while the negative end, which is the any end of the diode, is connected also to the negative end of the voltage source. Okay, so therefore this diode is forward biased. Okay, so in a forward biased mode, the diode conducts current represented by the direction shown by the number 1, the arrow labeled 1. So current is going to flow like that through the resistor up to the point of low potential. Okay, so we are saying during the first half cycle, in which this end is positive, the diode is forward biased, therefore it conducts electricity. So the diode will allow electricity to flow through the resistor up to this point. Okay, so the current is going to flow through load L, resistor L, building a voltage across it, which then decreases to 0 as the first half comes to an end. So the first half ends here. Okay, but if you look at this time, if we call this end positive, the lower end of the voltage source, the secondary coil, as positive, this is what is going to happen. Okay, so if this is at higher potential than this end, then what we have done essentially is that the connection of the diode with respect to the voltage is such that this negative end now is connected to the positive end. So remember that when a diode is connected to a positive terminal of the voltage source, it does not conduct. Okay, similarly, if you look at the positive end, which is this part here of the diode, is also connected to the region which is at lower potential. Okay, so in that case again, it's like now the diode is connected in a reverse mode. Therefore, it will not conduct. It will offer high resistance. So during the second cycle, we are saying, during the second cycle, which is considered to be negative, all right, the diode is reverse biased, and so it does not conduct electricity. So in so doing, it means we have rectified, we have changed the alternating current now into direct current. In other words, we have cut off the lower part, the negative part of the current, so that it is only in one positive direction. Okay, so the voltage output for half-wave rectification when connected to a CRO is simply shown by this diagram here. Okay, this is what you would see on a screen, on the cathode ray oscilloscope screen. You see half wave, half of the wave, because the lower part has been taken away by the use of the diode. They may ask you in an exam to state the disadvantages of rectifying current like this. Okay, so one of the disadvantages is that the output current is not smooth, meaning that the current is not perfectly flowing in a straight line like this. No, it has what we call some ripples. It's uneven. It is behaving like this. So this is not smooth. Okay, in other words, the direct current is not perfectly direct. Okay, it's not like it's traveling in a straight path. No, it has these ripples, so it's not smooth. The absence of smoothness in this case may result into some current being lost in form of negative ripples. Okay, so in this case there is need for us to devise a mechanism of smoothing it. We shall see how this can be done by using a special device which is called a capacitor. One of the uses of a capacitor is to smoothen a rectified current, because the direct current, once rectified, the alternating current, once rectified, does not flow in a perfectly straight line. It forms ripples. So those ripples are supposed to be removed by the action of an additional device, which is a capacitor. That's disadvantage number one of this process, of this method. All right, the other disadvantage is that there is much power loss, as one of the half cycles is eliminated, is lost. So by cutting off the lower part, the negative part of the current, we are basically losing some power. Remember that power from somewhere, remember that power P can be calculated as a function of current, I squared R. Okay, or current squared times R times resistance. So since we are cutting off the lower part of the current, it means some power is being lost because of the part which has been removed by the diode. Okay, so we are saying that if you consider this part here, you see only the positive part is shown. It means there's a part down here which is eliminated. So this part here is eliminated. Let me show you properly. We are saying that once rectified, we are going to have a wave like this. Our current is going to travel like this. So what does it mean? It means that the part which has been eliminated, which is the bottom part here, is accompanied or associated with power loss. Okay, so this removal of this part here results into power loss. That's a disadvantage of half-wave rectification. So once again, in an exam, they may ask you to explain the half-wave rectification. Please don't forget to say these points, and if in case they have asked you for a diagram, indicate very well the diagram that we have here, which is basically a transformer connected to a diode and then connected to a load. Load is just a resistor there. Okay, so that's what you can explain. Usually such a question may have 6 points or 6 marks, and then make sure that you know the diagram very well and the points associated with the diagram. In case they ask you for disadvantages, also don't hesitate to give the 2 disadvantages that we have discussed. My name is Mr. Paul Chilola once again. Please, in case you have questions, don't hesitate to contact us, to comment in the comment section below, or send us a text message on the number that has been given. All right. Also, don't forget, if you're new to the channel, subscribe to the channel so that you receive real-time updates and videos as we upload them. Alright, so in order to overcome the power loss by use of a single diode or a half-wave rectification, let us look at how that can be overcome by using a full-wave rectification approach. So, a full-wave rectification, take note, is done in two ways. We can use two diodes and what is called a center-tapped transformer, or you can use a bridge circuit, which is also called a bridge rectifier. In a bridge rectifier, we use 4 diodes. Okay, so I'll take you through the two types of full-wave rectification. One using 2 diodes and a transformer, and the other one just using 4 diodes connected in a bridge. Okay, so full-wave rectification using 2 diodes and a center-tapped transformer. Just like we saw with a half-wave rectification, where a transformer is used, in the full-wave rectification, we can also use a transformer which is tapped at the center. Okay, so this is the center of the transformer where current is tapped from. Okay, so 2 diodes are connected in such a way that each conducts current through a resistor load during a particular half cycle as shown. Okay, so once again, in a transformer we have an AC source, which is an input current in the primary coil, and this will induce a current in the secondary coil, such that one end of the secondary coil can have a higher electric potential or higher voltage than the other end. Take good note of that. So to show this, we call one end positive. We call one end positive, the other end negative. This is important for you because it will show you how a diode plays a part of rectifying. Okay, so 2 diodes are connected in such a way that each conducts current through the load L. This is the load, which is a resistor, during half cycles. Okay, so during the first cycle, we consider this part here, which is positive and is connected to a positive terminal of the diode. Remember, when you connect a positive end of the diode to a positive end of a voltage source, we say that it is forward biased. So current is going to, the diode is going to conduct in such a connection. Take note, you need to get this right. We are saying this end of the diode is positive, this end is negative. This end is positive, this end is negative. Alright? So, during the first half cycle, the diode D1 is forward biased. Why is it forward biased? Because the positive, the P part, which is the positive end, is connected to the positive potential. I don't want to use positive terminal because it's not a battery, it's a transformer. But one end is at higher potential than the other, meaning it is positive and the other end is negative. So when positive end is connected to positive end and the negative end, which is this one here, is connected to negative end, if you follow this, then current is going to flow through D1 like this. Notice that it is not going to proceed beyond B, point B. Current from D1 will not proceed through point B to D2, no. because this end is negative. So a negative and a negative block each other. Okay, in other words, this negative with respect to the positive there will make a reverse bias. So this D2 is blocking the current coming through point B there. So the current is going to proceed to the resistor and back to complete one cycle. So what are we saying? We are saying that during the first half cycle, D1, which is this diode, is forward biased, and D2 is reverse biased. Therefore, the path that current is going to take is from A to D to B, then through resistor, the load resistor L, to C and back to A. So this is the path that the current is going to follow. It will not go beyond B to pass through D2, no, because this is negative terminal, and it is, if you follow this direction, it is connected to the positive terminal of the voltage source. Therefore, this D2 cannot conduct. Okay. Similarly, if we take this end to be at higher potential than that end, if we take point D to be at higher potential than that end, then current is going to flow from D to D2, then through point B, and then through the load and back to D. Take note of that. So during the next half cycle, D2 is forward biased, while D1 is reverse biased, and the path of the current is now from D to diode D to point B to the load and back to C and then to D. All right. The current, notice that the current will not go beyond the B to diode D1 to A, no, because with respect to any end of the diode, this end is going to be negative, or it's going to be blocked. The current is going to be blocked by the negative end there. Okay, so it will not conduct. All right, so that's basically how full wave rectification is done using two diodes and a center tapped transformer. So after rectification is done, now the current is going to behave like this. The wave that will be shown, the output voltage signal, will be shown like this. The part that we have removed, or that has been removed by the two diodes, is this part here, the lower part. Take note of that. So this part has been removed, or it has simply been pushed up. Similarly, this part, the part which we had down here, has also been pushed up. So instead of being cut off completely, this part, it has simply been pushed into the positive direction. Therefore, here power is not lost. In this particular rectification process, power is not lost, unlike in the half-wave rectification using a single diode. All right. So you can say that full-wave rectification using two diodes and a center-tapped transformer is more advantageous than half-wave rectification, because power is not lost in the full-wave rectification. Okay, power is not lost. So please know the full-wave rectification using a center-tapped transformer and the two diodes, and the advantage of it over half-wave rectification, where only a single diode is used. Okay, and also be familiar with the wave function which is produced. They will ask you to show in an exam to draw a graph to show what wave function is going to be generated. So my name once again is Mr. Pochilola. Please don't hesitate to subscribe to the channel so that you get real-time updates. Okay, lastly, let's look at the full wave rectification using 4 diodes. When 4 diodes are connected like this, the circuit is called a bridge. It's a bridge circuit. Notice also that we have a transformer which brings in an alternating current. So once again, just like we saw in earlier rectification methods, when the current is brought into the primary coil, which is this, an EMF, also a current is induced in the secondary coil, such that one end is at higher potential than another. All right. Okay, so if we consider this end as being at higher potential, okay, as being at higher potential, all right, then what does it mean? With respect to the diodes, you'll notice that diode number 1 is directly connected to the region of high potential, voltage potential there. So we are saying if we consider this as positive, then it's diode 1 here is also positive, then this end is negative. That means D1 is connected in a forward biased mode. In other words, current is going to conduct. But upon reaching point B, when current reaches point B here, it cannot proceed to diode 2. Diode 2 will block it because this is negative, okay, with respect to the source, to the voltage source. This is negative and reverse biased, so D2 will not conduct. So current will simply follow the path from the voltage source through point A, then through point B, then it will proceed to the resistor like that, and then to D, and then to D3, and then back to where it came from. So take note of that. Just follow the coloring, the color codes that I've used. All right, so in this case, we are saying that, what are we saying? We are saying during the first cycle, point A, which is this one here, is positive with respect to point C. Is positive with respect to point C. Point C, this one. Okay. So diodes D1 and D2 are forward biased. So D1 and the D2, where is D2? Sorry. It should be D1 and D3 are forward biased. D1, if you follow this path up to D3, they are forward biased, okay? So that current therefore is going to flow along point A or path A to D1, then B, then through the load, the resistor here, and then to D, then through D3, then back to A, like that. The path that I've labeled with blue ink. Take note of that. So we are saying point A is positive, and the Therefore, it is the D1 is going to be forward biased. So current will be able to flow through this. But this current will be blocked through D2. The current will not flow through D2. It will proceed to the resistor, go to point C, and then proceed all along to point D. With respect to resistor D4, it is reverse biased, so it will not pass through, current will not pass through D4, but it will proceed to D3, then continue up to back to A. That's during the first cycle. During the second cycle, point A, you take point A, this one as negative, with respect to point C, and diodes D, only diodes D2 and D4. If this is positive, if this end is positive and that is negative, only D2 and D4 become forward biased, while D1 and D3 are reverse biased. Therefore, current will flow along the path C. Follow the diagram. Point C, from point C to point D2, C to D2, and then to point D, then through the resistor DL, then back to D, and then to D4, and then back to A. Okay, back to A, and then back to point C, back to point C, back to point C, back to point C. Very important. So during both half cycles, current flows through the load resistor in the same direction. All right. So that's the rectification process using 4 diodes. Please follow on the discussion and the diagram for you to appreciate what we are saying. So rectifier that is made up of 4 diodes has advantages over 2-diode rectifier in that a smaller transformer can be used. So here we can use a smaller transformer because there is no need for center tapping. Okay, in the other one, the way I used 2 diodes, we needed to tap current from the center, so we need a bigger transformer there. So a smaller transformer can be used because there is no need for center tapping. Okay, and also this bridge circuit is suitable for high voltage regulation where you need to handle higher voltage. It is possible to do that because we have a number of diodes in the circuit there. Now, like I mentioned earlier on, that the rectification is in most cases not smooth. The output current is not smooth. Okay, it is in form of a ripple like this. You have ripples. It's not a straight line, in other words. Okay, so in order to make sure that the rectification is smooth, we need to have a capacitor. So a capacitor is connected across the resistor R in order to smoothen this. All right. So connecting a capacitor through here. In fact, the capacitor will be connected through this across this terminal, across this resistor. Capacitor is something like that, so that the current, the output current, is as made as smooth as possible. In other words, without ripples like this. In other words, converting it into a perfectly linear current, okay, in flowing in one direction. All right, so I would like us to stop now. In case you have questions, don't hesitate once again to channel your questions in form of comments below the comment section, or you can simply give us a text message. We'll be able to respond to you. My name is Mr. Poechilola. Bye-bye.